Hello, everyone. I'm Jifei from FS, Shanghai Jiao Tong University. This talk will introduce our work, HTMFS, the first HTML-based persistent memory file system. In the early days, file systems are designed for performance with loose consistency guarantees. For example, FFS relies on the clean amount of the file system to avoid consistency issues. In case of crash or power shortages, file system users have to invoke and wait for the lengthy file system consistency checker, that is FSCheck, FSCK, which will detect consistency issues and attempt to recover, but without any guarantee. Nowadays, with the speed up of storage devices and their widespread use in applications, performance is not the only feature that applications need. Applications also require strong consistency in order to provide reliable service. For example, key value stores and databases need strong crash consistency to guarantee that all returned writes are persisted and can be correctly read after a system crash. Upon file systems with no or weak consistency guarantee, these applications have to either compromise on the consistency level or use complicated mechanisms to provide reliable storage. The strong consistency of the file system implies per request sequential consistency, which consists of two aspects. First, for arbitrary file system requests, the modification to the file system states observed by concurrent tasks should be atomic. Most file systems use inode level locks, which ensures the modification order of different requests to guarantee sequential consistency. Second, whenever the system crashes after a reboot, all previous file systems requests should satisfy the all or nothing semantics. That is, all changes to the file system state by a single file system request should be applied, or none of them should be applied. For example, if we have a file filled with character A, and then we invoke a write file system call to overwrite the file with character B. If a system crash occurs during this process after reboot, the data of the file should be all character A or all character B. However, file systems do not necessarily guarantee strong crash consistency. Suppose a writer crashes halfway through writing, it is possible for a reader to read the partial updated value after the system recovers. At the same time, modern storage devices have become faster and different. The emerging persistent memory enforces memory with durability. Consequently, file systems can use node or store instructions to access PM storage with near DRAM performance. Several PM file systems are proposed to exploit the PM characteristics. Many of them provide strong consistency. However, providing strong consistency guarantees is challenging for PM file systems because modern CPU and memory systems may reorder stores to memory, and the atomicity unit has changed from a block to a cache line. Previous approaches are limited to the atomicity unit of CPU writes. Intel's restricted transactional memory, RTM, can provide atomicity of multiple updates. We can wrap several memory access with xBegin and xEnd. If the transaction commits successfully, all changes will complete atomically. If the transaction fails for some reasons, nothing will be changed. It seems like HTM inherently satisfies all or nothing semantics. However, PM file system is incompatible with RTM naturally. Although persistent memory can be accessed directly by CPU node or store instructions, the PM write operation need to be persisted with the help of cache line flush instructions, such as cache line flush OPT, and cache line write back, which will abort the RTM. Recently, Intel proposed its second generation Optimum persistent memory products, which in cooperation with the new Xeon platforms enable enhanced asynchronous DRAM refresh technique, that is EADR, that embraces the CPU cache in the domain of persistence in case of crashes. In particular, the platforms guarantee the persistence of memory writes once they become globally visible, which means that data modification to the persistent memory no longer requires cache-line flush for persistence. This gives us the possibility of combining RTM and persistent memory to provide atomicity, concurrency, and persistence at the same time. Compared with traditional strong crash consistency mechanisms, RTM does not have the double write problem of journaling and does not require atomic replacement by merging all changes into one root node as in shadow paging. Therefore, there is a theoretical performance gain. However, several challenges prevent RTM from being used directly in PM file systems. At first, users use file systems to process large data storage and retrieval. However, RTM is limited in both read and write set size, thus can easily abort due to file data copy. Second, there are certain dependencies in the code path of FS-related system calls. For example, path-related operations such as open and makedir must be preceded by path lookups, and file indexing must be done before reading and writing a file. The operations can be lengthy and may include memory access that do not need to be tracked by RTM. Simply wrapping the entire operation within an RTM not only easily leads to capacity abort, but also increases the probability of conflict aborts. Next, we will first introduce HOP, hardware-assisted optimistic persistence. It is a lightweight hardware-software cooperative mechanism, and then we will describe how we use HOP to build HTMFS. We observe that all memory access in the file system operations can be classified into 3 types. 1, reads, 2, invisible writes, that is, updates that cannot be observed via the file system interface, such as memory allocation and updates to the shadow pages. And 3, visible writes, updates that can be observed by the file system interface, such as timestamp modification, in-place updates, and the change of file size. To alleviate the capacity aborts caused by complex file system operations, HOP splits a single file system operation into multiple small pieces and only wraps the visible writes in the transactions. Invisible writes are designed to be able to roll back with minimal overhead, while critical reads are protected by sequence counts. When joined together, these small pieces will perform similar to a single huge transaction, which is similar to transaction chopping. For example, a write file system call may allocate new pages, copy data to new pages, and modify the metadata in sequence. Each step is able to be classified according to the roles. However, there are still some problems when using HOP in the file system that require us to make some modifications to the file system. The first is that the size of the data copy can exceed the size of the write set of HTM. And should we wrap the memory allocation in the HTM? If we put it into the transaction, then concurrent memory allocation may abort the transaction. And if we leave it outside after a system crash, the allocated pages that has not been linked in the file system tree may be leaked. At the same time, we observe that transactions could have been used to handle concurrent access. HTM can help us to get strong crash consistency while also solving concurrency problems. For file data, we add a sequence count before each pointer and uses the sequence count to protect data read. For data write, a single page update is performed directly wrapped in a transaction, while multi-page updates need to allocate new shadow pages for the data and then copy the new data to the shadow pages. Pointers and corresponding sequence counts are updated atomically in an RTM. Next, we design an atomic memory allocator to prevent a memory leak after a crash. This is the structure of a free list. Our free list head will occupy a page. The first 8 bytes are a pointer to the current position and a pointer to the next chain. This is followed by some pointers to up to 511 free pages. In addition, our allocator is per thread, so there is no contention for concurrency access. Each thread has a free list for allocating new space and an allocated list indicating the pages that have been allocated but not yet persisted. When we need to allocate a new page, we just allocate a page from the free list and record it into the allocated list. When we need to persist the memory allocation, we just drop the allocated list in the same HTM with other visible writes to persist the allocation atomically. If crash happens before the memory allocation is persisted, HTMFS simply links the allocated list to the free list after reboot. For the directory entry, we use a hash-based structure to improve the scalability. Rather than inode level lock, we use per bucket sequence count to improve the scalability. When there are several concurrent threads, as long as the target names are hashed to different buckets, they can be executed correctly and concurrently. Rename is a special operation that requires atomically removing a directory or a file from the file system tree and adding it to another directory. Usually, we will hold locks on both directories to ensure the correctness. However, taking only the locks of the 2 directories modified cannot prevent the occurrence of a cycle. So some file systems have a global rename lock to prevent the rename cycle. Instead, we avoid the problem by checking all sequence count for the entire path from the root directory to the current operating directory. We implement HTMFS based on ZeroFS because it is a user space file system and all file system logic is implemented in libfs. We only modifies the libfs. Next is the performance evaluation. Our tested configurations are shown as follows. We compared HTMFS with several state-of-the-art file systems. First is a macro benchmark named FxMark, which is used to evaluate the scalability of file systems. The figures show the results in data rate in no contention level. It shows that HTMFS rate performance is the same with ZeroFS. For the data write in medium contention level benchmark, HTMFS has best performance and scalability, as shown in the right figure. However, when there is only one thread, ZeroFS is faster than HTMFS because the move instruction used by ZeroFS is faster than HTMFS when all writes hit the cache line. For the rename macro benchmark, when the contention level is low, HTMFS performs similar with ZeroFS. While the contention level increases, only HTMFS performance can continue to rise as the number of threads increases. The performance of HTMFS is similar or even better than that of a weak crash consistency file system. Next are 2 real-world applications. The first is TPCC on SQLite. The figure shows the throughput of different file systems. We can see that HTMFS and ZeroFS perform best. HTMFS is as good as ZeroFS, while Nova Remix is much better than Nova Copy and Write. The next application is LevelDB. The figures show the latencies of different write operations. It proves the previous conclusion again that HTMFS gets strong crash consistency for nearly free. To conclude, EADR gives us new opportunities to use HTM to guarantee crash consistency for PM file systems. However, the write set of HTM is limited, making it hard to use HTM directly. We propose HOP to provide strong crash consistency and fine-grained concurrency control simultaneously. Further, we apply HOP to build the first HTM-based user space PM file system named HTMFS, whose performance is comparable to or even better than state-of-the-art weak crash consistency file systems. That's all. And thank you for listening.